Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. Today's topic is illustrative examples of refrigeration system. This is the 40th module of the course Thermodynamics and its Application. I am Subhashish Maji, Professor in School of Engineering and Technology from Indira Gandhi National Open University. After listening to this video lecture, you will be able to understand the concept of various refrigeration cycle, and you will also be able to solve the numerical related to various refrigeration cycle. So, dear learners, let us begin our discussion on the illustrative examples of the various refrigeration cycle. Let us begin with the first numerical. An ideal weight compression refrigeration cycle with R12 as the refrigerant operates between an evaporated temperature of -10 degrees centigrade and a condensate temperature of 40 degrees centigrade. Calculate the following: refrigerating effect, compressor work, and COP, that is coefficient of performance. Dear learners, I had already given you the instruction for solving any numerical on thermodynamics. First of all, let us see what are the data given for any numerical, and after that, if you can draw the pH diagram or TS diagram or PV diagram for that cyclic process, then things will be more simpler. For this problem, the system is operating on the cycle as shown in figure 1, where TH is equal to 40 degrees centigrade and TL is equal to -10 degrees centigrade. The required properties of R12 can be read from the standard refrigeration table. So here you see that H2 is on the saturated vapor line, so at a higher pressure, so or at a higher temperature. So in this case, the value of H2 that is on the saturated vapor line we can get from the table, that is equivalent to Hg, that is enthalpy at the saturated vapor line corresponding to the temperature of 40 degrees centigrade. From the table, you can get this value of H2 is equal to 203.05 kilojoule per kg. H3 again is the point which is on the saturated liquid line corresponding to the temperature of 40 degrees centigrade, that also you can get from the table. H3 for this case you will get from the table, that is equal to 74.53 kilojoule per kg. Now H3 is equal to H4. Once you know the value of H3, that is equal to the value of H4. For this case, H3 is equal to H4 is equal to 74.53 kilojoule per kg. Now, how to calculate the enthalpy at the point 4? That you have already calculated, because in the expand process, the enthalpy remains same. So H3 is equal to H4. Now how to calculate the enthalpy at this point 1? Because 1 to 2 is the isentropic process. So entropy at the point 2 is equal to the entropy at point 1. So S2 is the entropy corresponding to the saturated vapor line of temperature 40 degrees centigrade. That value you can get from the table. So we know very well that S1 is equal to 1 minus x1 SF plus x1 multiplied by Sg at minus 10 degrees centigrade. What is x1? That is nothing but the dryness fraction or quality of the refrigerant. So S1 is equal to S2. S2 you can get from the table value, that is equal to 0.6820 is equal to 1 minus x1 multiplied by 0.1079 plus x1 multiplied by 0.7014. If you perform some this calculation for x1, that value comes out to be x1 is equal to 0.967. Now you can calculate H1 because you have already calculated the dryness fraction at the point 1. So H1 is equal to 1 minus x1 HA plus x1 multiplied with Hg corresponding to the low temperature, that is minus 10 degrees centigrade. So if you calculate H1, that comes out to be 177.9 kilojoule per kg. So the net refrigerating effect is equal to H1 minus H4. Dear learners, you have already calculated the enthalpy at state 1. You have also calculated the enthalpy at state 4. So there is no problem for calculating the refrigerating effect. For this problem, if you put the value of H1 and H4, you will get the net refrigerating effect is equal to 103.37 kilojoule per kg. Now next part is compression work. The compression work is nothing but H1 minus H2 is equal to 203.05 minus 177.9, because the value of H1 as well as the value of H2 are known at this point. So the compression work is equal to 25.15 kilojoule per kg. Now dear learners, now next term is we have to calculate the value of COP. You all know that coefficient of performance, that is COP, is equal to refrigerating effect divided by the compressor work. So the refrigerating effect is equal to 103.37 and the work done by the compressor is equal to 25.14. Just put these values in the expression for COP and finally you will get the value of COP is equal to 4.11. Dear learners, let us start with a very interesting numerical, that is, what is the maximum COP for a refrigeration system operating between minus 10 degrees centigrade and 40 degrees centigrade. B part of this problem is if the system is operating with R12 as the refrigerant, find the refrigerating effect and the compression work. And the last part is compare the results of A and B with those of exercise 1. Now I have already given you the instructions or advice how to solve any problem on thermodynamics. So here is the pH diagram. So the compression process is in between 1 to 2. The net refrigerating effect that you can get from this diagram, that is H1 minus H4. The turbine work is H3 minus H4, and let us see the expansion process, that is from the process 3 to 4. So during the expansion process, you know very well that the enthalpy doesn't change. So the enthalpy at point 3 is equal to the enthalpy at point 4. So from this diagram it is very clear that H3 is equal to H4. Now let us see how we can proceed for this problem. And this is the diagram for the Carnot refrigeration cycle. And you know very well that the maximum COP will get when the cycle operates on reverse Carnot cycle, that is for Carnot refrigeration cycle. Now in this case you see that the compression process is 1 to 2, that is isentropic process, and in this case the 3 to 4 star, that is also compression process, but the actual process, that is 3 to 4, that is during the process which is going on for expansion process due to the refrigerant passing through the expansion device. So for maximum COP, the system must be operating in a reversible cycle. On a reverse Carnot cycle, in such a case, that is COP is equal to TL divided by TH minus TL. So the cycle operates between the two temperatures, which is already given for this problem. For this case, TL is equal to 263 Kelvin and TH is equal to 313 Kelvin. Put the value for TL and TH and calculate the value of COP. For this problem, it comes out to be 5.26. Now, number B part of this problem says that the cycle can be assumed to be the same as 1 to 2 to 3 to 4 star to 1 in figure 3. Also COP is, we know that is equal to 5.26 is equal to net refrigerating effect divided by the net work done, that is equal to H1 minus H4 star divided by H2 minus H1 minus H3 minus H4 star. So when H1, H2, H3 have the same value as in exercise 1. Now put all these values, you can calculate H4 star, that comes out to be 69.53 kilojoule per kg. So net refrigerating effect is equal to H1 minus H star. If you put the value of H1 and H4 star, the net refrigerating effect comes out to be 108.37 kilojoule per kg, and the net work is equal to the refrigerating effect divided by COP. You know COP, you know refrigerating effect. So the net work for this problem is equal to 20.6 kilojoule per kg. The result in exercise 1 and exercise 2 are presented in the table. So the COP for the exercise 1 is 4.11, but for exercise 2 it is 5.26. The refrigerating effect for exercise 1 is 103.37, but for exercise 2 is 108.37. The work input for exercise 1 is 25.15 and for exercise 2 it is 20.6. The above table reveals that while the refrigerating effect and COP in exercise 2 are greater than those in exercise 1, the work input is similar. The difference between the two is because while the cycle in exercise 2 is reversible, the cycle in exercise 1 is not. Now let us begin the next numerical, that is exercise 3. Redo exercise 1 assuming dry compression and the enthalpy after compression is 209.4 kilojoule per kg. So here the compression process is from 1 to 2. So at state 2 the enthalpy is given, that is H2 is given as 209.4 kilojoule per kg. Dear learners, First, you draw the TS diagram and see how we can proceed for solving this numerical. The TS diagram of figure 4 may be used for the solution of this problem. Reading the required properties from the property table, H1 is equal to 183.06 kJ per kg, H2 is 209.4 kJ per kg from table, and H3, here H2 is given, that is equal to 209.4 kJ per kg, and H3 we can get as HF at 40 degrees centigrade from the table, that is equal to 74.53 kJ per kg, and H4 is equal to H3 because in the expansion process the enthalpy doesn't change. So H4 is equal to H3 is equal to 74.53 kJ per kg. So refrigerating effect is H1 minus H4, that comes out to be 108.53 kJ per kg. The compression work H2 minus H1, that comes out to be 26.34 kJ per kg. The COP of refrigeration system, that is equal to net refrigerating effect by compression work, that comes out to be 4.12. Now let us begin the exercise 4. It says that redo exercise 3 assuming compressor efficiency is 0.8. So dear learners, the process from 1 to 2s is isentropic process, but because of the irreversibilities in the system, the actual work done by the compressor is H2 minus H1. So 1 to 2 is the actual compressor work because of the irreversibility in the compression process. So this is the TS diagram. Here the compression process is not reversible as its efficiency is not 100% but is given to be 80%. Hence, more work is required by the compressor during this irreversibilities adiabatic compression process. The efficiency of a compressor is defined as the ratio of the reversible adiabatic work of compression to the actual work, the compression occurring in both the cases from the same initial state to the same discharge pressure. So figure 4, while 1 to 2s is the reversible adiabatic compression process, 1 to 2 is the actual compression process. Thus W1 to 2h. So here the actual reversible work done divided by here the reversible work done divided by the actual work done is defined as the efficiency. So now we can see how we can proceed for this problem. The state 2is the same as state 2 in problem 3, that is exercise 3. Therefore, W reversible actual is equal to H2s minus H1 is equal to 26.34 kJ per kg, and the value of H1 is 183.06. So from the expressions for the efficiency of the compression, we can write 0.8 is equal to the reversible work divided by the actual work. So actual work we can calculate, that comes out to be 32.955 kJ per kg. The refrigerating effect is equal to H1 minus H4, that comes out to be 108.53 kJ per kg. The coefficient of performance is equal to refrigerating effect divided by the compressor work. For this case, coefficient of performance is equal to 3.3. Dear learners, let us start with a very interesting numerical. And refrigerant 1-2 refrigeration plant of capacity 17.5 kilowatt maintains a cold store at minus 20 degrees centigrade. The condenser cooling water is available in plenty at 30 degrees centigrade. The enthalpy of refrigerant vapor at the end of isentropic compression is 206 kJ per kg. Find COP, the mass flow rate of the refrigerant, the compressor power and compressor cylinder dimension assuming stroke is equal to 1.2 diameter. Speed is given equal to 900 revolution per minute and volumetric efficiency is 0.92. Figure 4 can be assumed to represent the cycle on which the system operates. Properties at various states can be found using the table of properties. H1 is equal to 178.61 kJ per kg. H2 is given, that is equal to 206 kJ per kg. H3 is equal to H4 equal to 64.54 kJ per kg. V1, that is a specific volume, is equal to 0.10885 meter cube per kg. Refrigerating effect is equal to H1 minus H4. We know H1, we know H4, so the refrigerating effect is equal to 114.07 kJ per kg. The compression work is equal to H2 minus H1 is equal to 27.39 kJ per kg. This is the T diagram for exercise 5. So here you see that the actual work done by the compression is H2 minus H1, but isentropic work done is equal to H2S minus H1. So the compressor efficiency is defined as isentropic work done divided by the actual work done, that will be equal to H2S minus H1 divided by H2 minus H1. Now let us see how we can proceed for this numerical. The COP is equal to refrigerating effect by compression work, that is equal to 114.07 divided by 27.39 is equal to 4.16. The mass flow rate is equal to capacity by refrigerating effect. Capacity is given as 17.5. Refrigerating effect, that is already we have calculated, that is equal to 114.07. Put the values of capacity and refrigerating effect, so we can calculate the mass flow rate. For this problem it comes out to be 0.153 kg per second. The compression work is equal to mass flow rate multiplied by the compression work per kg, that comes out to be 0.1543 multiplied by 27.39 is equal to 4.19 kilowatt. So speed of compressor is given as 900 revolution per minute, that is equal to 15 revolution per second. Specific volume of refrigeration at state 1, vapor at entry to compressor is equal to V1, that is equal to 0.10885 meter cube per kg. The actual volume of vapor handled per second is equal to mass flow rate multiplied by V1, that is equal to 0.01665 meter cube per second. As the compressor runs 15 times per second, the actual volume of vapor handled by the compressor per cycle is equal to 0.01665 divided by 15, and the piston displacement volume is equal to pi by 4 d square multiplied by 1.2 d. Here d is the diameter of the cylinder and 1.2 d is the stroke length. So the volumetric efficiency is equal to actual volume handled divided by piston displacement volume, that is given as 0.92. So we can put the value of volumetric efficiency, that is 0.92, equal to the actual volume displacement by piston volume is, so we know the volumetric efficiency is equal to 0.92, and we know very well that the volumetric efficiency is equal to actual volume handled divided by the piston displacement volume. So from this expression we can calculate the diameter of the compressor cylinder, that is equal to 10.85 centimeter, and the stroke length is equal to 1.2 d, that comes out to be 13.02 centimeters. Now let us discuss the exercise 6. A power cycle uses refrigerant 1,2 as the vacuum fluid. It operates between the pressure of 60 kilopascal and 600 kilopascal, and the states at the process endpoints are shown in the pH diagram. The quality X3 is equal to 0.8. Find COP, mass flow rate of the refrigerant, and the compressor power. Now here you see the diagram, we can calculate the enthalpy at 1, Q, and also the other points. So H3 is equal to 1.62.69 plus 0.8 into 170.19, because the dryness fraction at 0.3 is given. So that comes out to be 2. Here the H3 comes out to be 298.802 kilojoule per kg. So H4 is equal to H1, that comes out to be 220.84 kilojoule per kg. So H2 is equal to 360.61 kilojoule per kg. So COP is nothing but refrigerating effect divided by the compressor work, that is equal to H3 minus H4 divided by H2 minus H3. If you put all these values, you will get the value of COP is equal to 1.2628. Mass flow rate is equal to capacity by refrigerating effect. Put the values of capacity as well as the refrigerating effect. You can calculate the mass flow rate. Here it is 0.135 kg per second. Compressor power, that is equal to mass flow rate into compressor work per kg. To put the values, you will get the compressor power, that comes out to be 8.34 kilowatt. Now let us discuss the last problem. In an aircraft cooling system, air enters the compressor at 0.1 megapascal at 4 degrees centigrade and compressed to 0.3 megapascal with an isentropic efficiency of 72%. After being cooled at 55 degrees centigrade at constant pressure in a heat exchanger, the air then expands in a turbine to 0.1 megapascal with an isentropic efficiency of 78%. How low temperature air absorbs a cooling load of 3 tons of refrigeration at constant pressure before re-entering the compressor, which is driven by the turbine. Assuming air to be an ideal gas, determine the COP of the refrigerator, the driving power required, and the air mass flow rate. For this problem, this is the block diagram. Here there is a compressor, there is a turbine, there is a place where the refrigerated space is there, and the cold air extracts it from the refrigerated space for making that space in a lower temperature. So this is the TS diagram for exercise 7. So the state 1 is the entry point of the compressor for the compression process, and the point 2 is the actual state after the compression process, and 2S is the isentropic compression process at the final state of the compression process, and so on. Now we know very well that the value of T1 is equal to 277 K, T3 is equal to 273 plus 55 is equal to 328 K, And we know very well that T2s by T1 is equal to P2 by P1 whole to the power gamma minus 1 by gamma. So we can calculate T2s. Here we will get it 379 Kelvin. And T2s minus T1 is equal to 102, and T2 minus T1 is equal to 102 divided by 0.72 is equal to 141.8. Similarly, T4s by T3 is equal to P1 by P2 to the power gamma minus 1 by gamma. Now T4s by T1 is equal to P1 by P2 whole to the power gamma minus 1 by gamma. So T4s is equal to T3 divided by P2 by P1 to the power gamma minus 1 by gamma. So after doing some algebra, you can calculate the value of T4s. For here, you can get the value of T4s is equal to 240K. So T3 minus T4s is equal to 88. So T3 minus T4 is equal to 0.78 multiplied by 88, that comes out to be 68.6. So T4 you will get 259.4 Kelvin. Now the refrigerating effect is nothing but Cp multiplied by T1 minus T4. You know T1, you know T4, so you can calculate the refrigerating effect. That comes out to be Cp multiplied by 17.6 kilojoule per kg. Net work input you can calculate from the expression. For this problem, it is equal to Cp multiplied by 73.2 kilojoule per kg. So COP is nothing but net refrigerating effect divided by work done. For this case, COP is equal to 0.24. Driving power required, that is equal to 3 multiplied by 14,000 divided by 0.24 multiplied by 3600, that comes out to be 48.6 kilowatt. The mass flow rate is equal to 0.66 kg per second for this problem. So dear learners, we have discussed in detail about the various refrigeration cycle, and also we have discussed how to solve the numerical related to various refrigeration cycle. Thank you very much. I wish you all the best for completing this course, that is thermodynamics and its application. Thank you very much.